my desktop. Okay. And I'm going to save credit approval new data to score as well. Thank you, guys. And then I'm going to, because when I leave Blackboard, it goes to 13 automatically. I save those files so that I will manually open JUMP. Okay. And then open this in 14.2. Okay. So you see, I should have one less problem in 14.2. So let me change this to a numeric nominal. Okay. This remains no and yes, but for what we're trying to do, this could be 0 and 1 as well. Now you see here, when I changed it, the data doesn't show. Oop. I should have, do Control Z. I should have changed this to zeros and ones. Okay, I want to put it back 0. The most time-consuming part of when you do analytics, and I'm proving that to you, is preparing the data to be in a way that is ready to be mined. Okay. Be careful so that you do not add an extra record by mistake. Okay, so this is the data. Analyze predictive validation, 0.6, 0.4. All right, so basically I'm starting over again. And this is good because now we are recording it. I did not plan it this way, it just worked out like that. I was going to do the same thing even if the thing was being recorded from the beginning. Analyze multivariate methods, discriminate. You see, you even have more options here. Okay, so let's copy, this is actual decision. I'm not going to go back and correct it now. Validation to validation, and copy this. In 13, when I move those columns to covariates, I got an error. I still get an error. So I will go here, double click, and I'm going to make this numeric. In 13.2, in 13, I got an error. In 14.2, I should not, if I remember correctly. Analyze multivariate discriminant, copy this into Y covariate, there you go. In 13, I was getting an error even when I made it numeric nominal. Okay, and that is why I want to be consistently in one version instead of, okay. So actual goes into X and validation goes into validation. Traditionally, the item that, usually the status quo is that when you have the dependent variable goes with Y. Okay, due to linear algebra things, it's reversed, but this may or may not happen. This doesn't happen with all software packages. Discriminant analysis is similar to logistics, which is one of the most powerful algorithms that we will start this Thursday. As I mentioned in my email, quizzes will always be Thursdays, regardless of anything that's going on. And the quiz this Thursday will be on what was going to be last Thursday, which is K and N. Okay? All right. So let me... Discriminant method, there are different discriminant methods, linear, using covariance. There's quadratic, and there's a couple of other ones. So let me click OK. Now, this gives you a warning. The following columns are not continuous, indicating a possible mistake. See, homeowner, right, has values 0 and 1. When you have a variable in statistics that has values like 0 or 1, what is that variable called? Continuous or discrete? It's discrete. Discrete is when you have discrete, a variable is discrete values, 0, 1, 2, all right? But it allows you to proceed. Continuous means a variable can have value like 0.2, 0.3, all possible values between 0 and 1. But that's okay. I could make it continuous, but I leave it like that. I say continue even with that. All right. So by canonical, I'm not going to go over this too much. By canonical variables are, remember when we talked about principal component analysis, those variables z's, those are canonical variables. And this is where everybody should have picked up one of these. I will tell you a little bit about, because this document deals with canonicals, okay? You will not be required, you will not be tested on this at all, but I went through this a little bit last time. This document, where is it? This is from that Said Sayad website. It's from this website. We're doing discriminant analysis, which is here, linear discriminant analysis. We're doing discriminant analysis, but we're doing linear, okay? And there's the document that you have a hard copy, okay? So when it talks about covariates, all right, in JUMP, these canonical variables, all right, canonical variables are these z's that that he discusses. These betas are calculated via linear algebra. I went through this quickly last time. I'm not going to hold you responsible, all right? And I went through this last time, and so these numbers right here, that's where, in fact, I used exactly the same example. So you have two of these, Z1 and Z2, and this is kind of what you see here as canonical 1, canonical 2. That's all I'm going to say. There's a little bit of linear algebra involved here, and so that's why I don't want to talk a lot about this. But I want to talk about most of the other stuff. So let me close things that I don't need. Okay. Discriminant scores. This V stands for validation data. So if I right-click up here, okay, if I right-click up here, and they sort by column, here you don't see headings, but this sample is the column that the heading for where you see V. If I sort by that, then you see this is my validation data, okay? Which you also have in the original table. All right? This is the validation data. And if I sort here by, oh, you see they were highlighted automatically. If I sort here by ascending, oh, I'm using this, then you can have the training and the validation, right? The reason this automatic highlight is because I was using them inside jump here. That's why. Okay. Now, the nice thing about when you select data, okay, I'm showing you a lot more than discriminant analysis here. I'm showing you some things about jump. If I select this data, see, you can take it and save it somewhere else. And the reason that I select this data here is so that I'm going to use them because right below this, it has, right below this, Control-Shift+ to make the font size bigger. I want to show you where these numbers for the confusion tables came from. And this is one way I can test you. I can give you this output, and I can tell you to generate these tables. Okay, now, so in the score summaries, you see it says there are 30 training records. The records that don't have a V, those are the training, right? If you count them from 1 to, well, these don't count them based on these numbers here. These are the actual raw numbers, but there's 30 of them, and there's 20 validation, okay? Now, out of the 30 records, 0 were misclassified. Well, what you can do, the nice thing here is that, you can click on this actual, hold it down. Oh, I thought I can move this. No. Well, misclassification is when the actual, this is actual decision, this is predicted decision. Okay? So if these two are the same, and you look at the training data, this is my training data, right? If you look at the training data, there's no misclassifications. All the no's are no's, and all the yeses are yeses. Okay? That's why you have 0 misclassifications. And ignore about the entropy and the -2 log likelihood. There is a meaning with those, but forget about those. Now, are you surprised that the misclassification is 0 with training data? No. It could be, the misclassification with training data is either 0 or very close to being 0. We're not surprised. Why? Because the training data, after all, was used to produce the model. Okay. Let's go to the validation data. If you look at the validation data, you have 2 misclassifications. You see the asterisk here? There's 2 asterisks, 2 misclassifications. 2 out of 20 for a 10% misclassification error, right? Again, ignore these 2. By the way, there is a, while I'm in jump, in the preferences, in the, if you go to here, JAP has something that will allow you to do annotate. It has something for everything. If I go to File Preferences, there's an option under Reports that says Laser Pointer Off. If I turn this to, I don't know, orange, yellow, green, so that when I produce a report, I can use the laser. And I don't know if it will allow me to use it here, but right click. Anyways, there should be a way to, so, but anyways, the 10%. Now, if you look at the validation data, okay, this is actual, this is predicted, but you see how they have the zeros first and the yeses second. I don't know if I can change those. No. Okay. So if you look at the validation data, right? If you select the validation data and then right click and say make into data table, you can make this into a data table which allows you, all right, and I mean you can delete if you want to the training data. Let's delete the training data. So I only have validation data, and I can move the actual, click on it and drag it and drop it there. Oops. I want to move the actual to the left of predicted. Click it, push it down. Anyways. Well, I want to have things sorted by predicted and actual. Okay, so I can say right click, sort, ascending. So you have the no's and the yeses. So you see here you have 1, 1, yes, yes, right? You have 1, 2, 3, 4, 5, 6, 7, 8. Oops, there's another one, 9. How did we miss that? Oh, okay. So you have 9 1 1s. Yes, yes. 9 yes, yeses. That's this 9. All right? You have, if you look at the no-nos, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. You have 9 no-nos too. No, no, 9. And then you have 2 no yeses. No, yes, 2 of them. These are the 2 misclassifications. That's where the 2 comes from. So you can create the confusion matrix from here. All right? You can do it yourself. All right. If you click at groups, you have 2 groups, no and yes, and you have 16 and 14. The groups refers to the training data only. After all, the training data has 30 observations, right? By an observation, when we say observation, okay, let's close things that we don't need. By an observation, we mean this is an observation right here. Homeowner, credit score, years of credit history, revolving balance, revolving utilization, right? This is an observation, and what we're trying to predict, we're trying to classify an observation as being either a no or a yes. Okay? You guys follow me? All right. Okay. I want to make sure that jump allows you to create incredible amounts of very useful output. And one of the things that it does at the same time, it creates a lot of output, a lot of windows. There may be a way to control that. So if you don't need something, close it, because it can get very busy very quickly. All right. So this is the discriminant scores. Groups, we have seen those. All right. What other things can I generate? I'm going to talk a little bit about this later on. We can do very similar things to what we did with a stepwise in multiple linear regression. We have different types of discriminant methods. We are talking about linear. These are the other types that you can play with. The white is if you have a very high number of columns. Okay. Quadratic is when if you're doing if your scatter plots look like a U shape. Okay. You may or may not need to show the discriminant scores, so you can take it away because it takes up a lot of space. Here is where you can do a lot of things. Show interesting rows only, and look at the help. Show only the rows that are misclassified. So if I displayed the discriminant scores, you see, I only see the rows that are misclassified. This is pretty useful, right? I see the validation, but this is misclassified. Apparently, it only does it for validation data because this is a no, this is a yes, this is a no, this is the training data. It shows the misclassified. Apparently, this applies. This applies to validation, or maybe or less. Anyways, let's not worry about that. I want to eliminate that from the output. Under score options, the classification counts are shown over here. Show distances to each group. Okay, let's see what that is. Remember that we have two different groups, zeros and ones. And so we have the two different groups. If these are the zeros, okay, and these are the ones, and this is the new observation. This is the centroid of class 0, centroid of class 1, and you see I on purpose do not make it the center because it doesn't have to be. When we are looking at this distance, at these distances, okay, these are the Mahalanobis distances. And so you take a look at these two distances, and it shows you that this is 3.3, and this is 19. You see, I did not draw this to be much, much bigger because this is statistical distance. It's not the Euclidean distance, right? So this is 3.3 statistical distance, and this is 19. So, but basically, this is the actual, right? I can predict the class, I can classify from just using this, predicted which class should observation 1, which class should we predict this observation to be, to no or yes? No, because that's the class that this observation 1 is these columns together. Okay? So it's very important to understand what observation means, right? So this is observation 1, right there. It doesn't include the decision variable. So this is row 1. Number 1 represents this. Okay, this is like a unique key identifier. It's like the primary key when you're working with a relation table. Okay. So observation 2 is classified with to which class? No. No or 0, right? So you see here, you can take a look at the smallest of the two value to this, when it says square distances, right? These are Mahalanobis distances to each group. Group 1, group 0, group 1. Okay. Right. Then I can score the probabilities to each group. Shows the tables of the probabilities to each group. Okay, so now you have probabilities. If I, once again, you have the two groups. You have the two groups. Group 0 or no, and group 1 or yes. One of the things that JUMP does not talk a lot about is the cutoff point. And even though there's a way to do it, I don't think that they have implemented this well into this version. It may be in version 15, but I will make a request that they include it. Every time they go into a new edition or sub-edition, they are programming people's requests, and the cutoff point somehow keeps being pushed down. So here is, again, observation 1, all right? So here is the new observation, or observation 1. This here is the probability that observation 1, okay, will be assigned to class no, to class 0. This is the probability that that observation 1 will be assigned to class 1. Okay. There's two different ways to interpret that, to interpret these two probabilities. You take what is the highest probability from the two? This one. So the observation is assigned to the class with the highest probability. Probability no again. Observation 2, probability no, and so forth. Okay? The most appropriate way to describe these probabilities is you take, so this goes with a 1, right? 1 or yes. you take the cutoff point by default is 0.50. It's cumbersome to look around and find out how to change this. They do say change it, but this is a feature that has not been programmed into the version. So what you do is you take this probability and you compare it with the cutoff point. Okay? In the document that I have online, I talk about this. I know it's somewhere. Okay. Here is using the distances, and here is using the probabilities. This is one way, and here is another. They're both basically, it turns up that no matter which one you use, you'll come up with the same result. But if this probability is less than the cutoff point, okay? So if the probability, yes, is less than or equal to the cutoff point 0.5, okay, then predict no. Predict no. If the probability of yes is greater than 0.50, then assign the observation to the yes class. Okay? So this is what it's really doing, but you can assign, you can also use this probabilities the way I explained. Assign the observation to the class with the highest probability. That's all. Okay? Okay. So that's the probabilities. I'm doing one thing at a time here. The ROC curve, you can have an ROC if no was the main thing, and here you have the two ROC curves. This is not so useful because I don't have a lot of data. and so, but this is, we know how to interpret it. You have 1 minus specificity here, or the FPR sensitivity here. So you want points to, the good points are the points that are close to, this is the ideal point. This is the best point. Discriminant score. Now, I want to have my table. Oops. This is my table, and this is the red triangle here, and I want you to see what happens next. So if I click here, score means doing everything around predicting records or scoring. If I click, look here, I don't have any columns, right? At the end. If I click Save Formulas, you're going to save some formulas here. And if I say Publish Probability Formulas, then I open up the formula depot. Okay? All right. Now, what are these formulas here? There's a 0 here. These formulas, these columns have formulas behind them. We have seen these two, we have seen them in the discriminant analysis red triangle. When I clicked square distances, see the square distances? I have them here. The probabilities to each group, I have them here. The groups are no and yes, or 0 and 1. Okay. If I right-click where it says square distance 0, this 0 has nothing to do with the class no, which is equivalent to 0. If I right-click here and click formula, this is the Mahalanobis distance. This is the distance of the observation to the centroid of all the observations together. Okay? So, so that is the Mahalanobis distance. It calculates that for us. The document that you have a hard copy of describes how to get it, and I quickly went over that last time. You have an Excel file that does these calculations, and you obtain the Mahalanobis distance. What is the Mahalanobis distance? Let me just get blank space. Okay. If I have two groups, two classes, two populations, those two can be overlapping, very overlapping, or they can be like this, or they can be far away. Do we want the groups to be far away or close or overlapping?
Far away.
We want them to be far away. Why?
To be able to distinguish.
Because it becomes easier to assign a new observation to a group. The Mahalanobis distance, delta, or whatever letter you want to use, is a number. If the Mahalanobis distance is greater or equal to 3, this is similar to 3 standard deviations. It's not really 3 standard, but if the Mahalanobis distance is greater or equal to 3, it means that the circles, the groups, are the greater the Mahalanobis distance number, the farther the groups are. So in this example that I did, the Mahalanobis is 2.32, okay, which means that it's a decent distance. I forget which is the minimum, which shows you that the loops, the groups overlap. But if it's beyond 2.5 to 3, then it's you want the Mahalanobis distance to be greater than 3, greater than 2.5, greater than 3. I will try to dig up meaning of Mahalanobis distance. I forget what the number. Oh, how many standard deviations? It is. Okay, it is how many standard deviations. Sorry. So, if you remember, if data is 3 standard deviations farther away from the mean, it means the data is on the tails, far away. And in this case, we want, it's a generalization. It's not exactly that, as I said, but it works in a similar way. But there is a number, minimum number. Anyways, I forgot what the minimum number is. But you want it to be, for us, if it's greater than or equal to 3, so it's not exactly the standard deviations, but it's similar to that. Many companies, if an observation is at least 3 standard deviations away from the mean, they call it an outlier. So in this case, we want the Mahalanobis distance to act like an outlier because it means that 2 groups are far away from each other. Okay, so very good. Okay, so this distance, so this number right here, 304, is the statistical distance of observation 1 from all of my 50 observations. Okay? From the centroid of all the observations. Square distance 0. Right click and click formula. This is the Mahalanobis distance plus, here you have these constants, this times homeowner, negative 0.68 times credit score, blah, blah. And there's a meaning to this number. My mind is not working very well today. This stands for something, I forgot what it is. But this is the distance, all of this together, the Mahalanobis plus this plus that is and there's a preview at the end, right? So, record 1, 763. Okay, I want to show you. All right. Let me make this right here. This is the actual table, right? Okay. So you see here, it says if the credit score is 625, so you want to make sure that I go to the credit score 625, homeowner is 0, revolving 1280, revolving utilization 65%, the square distance, the Mahalanobis is 304, that's this one up here, years of credit history 15, I don't know how it picks up the columns to be that, and the distance 3.33 is the right here. This is the distance of observation 1 from group no. Right? Then 527, 4.1. You see these numbers are these numbers here. Okay. I expect you to be able to explain the output. That's what I'm doing here. All right. Similarly, you have the square distance to group yes. So it's the many windows that drives me a little bit crazy. But then again, if we want to have a lot of data, useful data to interpret, this is going to happen. So I prefer to have this problem than one that gives me a little bit of output, all right, and I cannot use it, right? Okay, so this is the square distance no. I right-click to square distance yes, and I pick formula. Here is another square distance. Oops. Here's another square distance. And that has a preview as well underneath that I can do, that I can use. Right? And so I have these square distances, right? And you want the observation to be assigned to the class with the shortest distance. These functions are called discriminant functions because using them, you discriminate. You say, this distance is smaller than that, so I will assign my observation to the class with the shortest. I discriminate. Okay? Yeah.
Do these functions place more importance on the distance or on the probability?
These two functions are using Mahalanobis distance. They're using the statistical distances. Using the square distances or the probabilities is exactly the same result. There is a formula for the probabilities. If I go to the probability, right-click and say formula, this is how this probability is calculated.
Based on the distance.
Based on these Mahalanobis distances. The important thing here is what, when I picked on Kyoka last time, and I said, who is the person farthest away from you, right? When you pick Dave, you're using the Euclidean distance. But when you pick the one where you are statistically close to, right? It could be you again, but you would be the person closest now, right? Then this is the formula used to calculate the probability of no, and it's using the Mahalanobis distance. Okay, and it's using it's one, you understand, this is e to the negative 5, right? You understand what this is, right? And here is a formula for the other probability. The formulas for the square distances are different than the formulas for the probabilities, but they produce the same results. And statistical distance is what is used behind the scenes, and that's the important thing here. But I keep forgetting what the heck this is. Somewhere I have it, I know. This under certain conditions, to minimize some bias, this is log something something. I will find out and I will let you know. So this is an added constant to minimize some type of a bias. But let me find out what that is. So the important thing is that we have saved these formulas to the table. This no can be produced by using the highest of the two probabilities or the smallest of the square distances. Okay? Very good. Okay. I have too many things open. Again, somebody may say, well, too many things, but I prefer to have a lot of useful things that I can do instead of having a simple output that does not help me. It always comes down to, do you know what you're doing? And if you know what you're doing, you will not be influenced if you have a few windows or if you have a lot. Now, going back here, score options, we're done with that. Canonical options, whenever it talks about canonical, this has to do with component, principal component analysis, those Z. Okay? Scatter plot matrix. Okay. So here is the scatter plot matrix. And you have a red triangle. Anytime you see a red triangle, click to find out what you can do. I can, let me make this bigger. Oh, that's too much. Control Z. Now, when you look at this, how can you quickly identify useful predictors? Can somebody tell me? Yeah.
By observing the relationship between the two.
Correct. And so, which of these and the colors? See, if you look at this picture and you don't know how to interpret it, you say, what the heck is this? But if you know how to interpret it properly, you say, excellent. How do I read these? And the reason they do the coloring is not to make it look pretty. It's to make it easier for you. Remember, remember the following. I want to do 4 of these pictures. Oops. 1, 2. This is why it's important to always review, and in real life as well, to review things that you have gone over before. All right. If you have a line that looks like this, this is X, this is X, and this is Y. This is X, and this is Y. So if you have a line that has a positive slope, what does it say about x and y?
Positive relationship.
Positive relationship, meaning as x goes up, so does y. As x goes down, so does y. But it says, when you say positive relationship, this also says that x and y are linearly related. That is, knowing this explanation is more important than knowing that saying that x and y are positive, are going in the same direction. If the line goes down like this, what can you say about x and y? Once again, they are moving in opposite directions, but once again, x and y are linearly related. When the slope is like this, or like this, what can you say about x and y? X and y are not linearly related. This is very important. This is very easy that we get to sidestep. X and y are not linearly related. All right? I cannot emphasize how important this is. And I told you the story about Lucy, my sister's friend, who I've been telling for 20 years people that she got $250,000 as a starting salary, and all that time I was incorrect. Within a couple of years after that, she was making $450,000, my sister told me. I just found this out 2 weeks ago. And Lucy retired at the age of 40. And I wanted to hear that because she was very good in understanding, in analyzing the data. So the thing is this, how can this, all right, this is very, very important. How can that help us here? I want to look at this oblong shape, oblong or egg shape, that look like these, you see? You see, when you see this, call them circles, whatever. When you see these circles, this means you have a positive slope. Means x and y are linearly related, which is credit score and revolving utilization. What about here? Do you have, this look like, if you draw a line through them, it looks like the slope will be closer to zero. Same here, slope close to zero, close to zero, close to zero, close to zero, close to zero. I want these circles to be at an angle like that. And when I see one of these, I go to the corresponding variables, all right? So this may not have, but this is the one, this is the kind of a bend or angle at which these groups, I want to see them at. If they look like this, so this is a negative slope, or they could look in a positive slope, right? So that's how I can use this in a very meaningful way. You understand what I'm talking about? Excellent. This is analytics, okay? And because once you identify a strong relationship between two variables, what do? You eliminate one of them. Why? Because having one represents both the variance the correlation between them will be high. So you do not want things to be highly correlated. That means anytime you don't have the circles this way or that way, so revolving balance and credit score are not highly correlated. So the likelihood is you want to keep both. These are very important statements. Okay. You can do other things here. If you click fit line, then you draw this line right there. And this shows you if you who is highly correlated and who is not. Very important. So I can give you a picture like that and ask you to tell me which variables are important, meaning you want to keep them, which are not important. Try to eliminate them. Okay? Get involved with anything AI. You can make a lot of money, especially if you have passion for this. If you have passion for this, having passion for something means that you do something without anyone rewarding you. Right? Without anyone rewarding you. When I see somebody like that, I tell them, regardless on which part of the world they are. I have a niece who has that passion. She's a medical doctor. She doesn't have to in Greece, but she wants to get a PhD outside of Greece. And this young lady is fantastic. She's sacrificing a lot. Okay? A colleague of mine, a friend, is visiting Israel, who's a tremendous scientist, who is also a scientist here at Northeastern, was in Greece, and I brought the two of them together so that see if my niece can come to the United States. She's also working, she does research on skin diseases, and her project has been approved by University of Berlin. And she may come here because a very good friend of mine who is in the biochemistry department, who's a tremendous scientist, was down there, and they met. So passion means that you don't say, I'll do it if you pay me. But see, if you do things and people see the passion, you will be rewarded. But no matter what, regardless if they see your passion or not, you will always be rewarded because you are happy doing it. So, passion means you jump in, you get to the bottom of things without expecting people to guide you. Okay, let me see if I... Show group means. This is another useful thing. You see, you have... by the way, this group means works only with the training data. I didn't pay attention in the beginning, it was driving me nuts. I am adding this to the homework, which is homework 8. I want you to, you're lucky I got sick because I forgot to add some other problems to your homework 8. I want you to find the average of group no, which is this. I'm adding that to homework 8. The average to group yes to be this. It's not a difficult thing, all right? So you have two groups, group 0 and group no, and group 0. Group 0, which is the no group, and group 1, which is the yes group. This is a nice little exercise. So this here represents the centroid of the no group, and this represents the centroid of this other group. I think you will like this exercise, little exercise. So basically, you have, this is the no group, okay? This is the yes group, okay? So, and this here is the centroid of all. So this is the centroid of all 50. Okay? So this is all 50 observations. So if you want to put all of them together, all right? So here is centroid for the no, here's the centroid for the yes, and here's the centroid of all. Okay, now, and here's a new observation. This distance here is the SQS dist 0 that you have in jump. So when you calculate this distance here, let me call this D, just a short note, all right? So this distance uses that plus the formula, okay, plus the formula plus the constant at the end, which is some sort of an adjustment, which I will dig up. Okay? So, and this here is your square distance no. Okay? Equivalent, so you see Mahalanobis distance is used very heavily. And equivalently, or similarly, you find the yes distance. Okay? One thing that I'm going to go to this. Ooh. That I want to, let me just say something with these distances. That if I go to this distance, to the formula, you see this constant right here? This constant right here. Oops. Whoa. Yeah. Oh. Okay. These constants right here are, you're not responsible for knowing. They should be provided somewhere, but these betas, you're not responsible for it, but these betas are this beta right here. Okay, you can find them. I'm not going to hold you responsible, but you can find them, and they're found using this I have this document in Excel file that I went quickly over it, all right? But they can be found. They should have been provided by JUMP. They may be provided somewhere, but I didn't find it. Now, in JUMP, we also have where is my formula? Okay, this is the formula depot, okay? And in JUMP, let me close things that I don't need. Close this. I have credit approval original. Let me open, because I've said the credit approval new data source. So these are new observations. These are new customers. and the bank needs to make a decision, should we approve the loan, yes or no? And you can have millions of them, right? So now that I've opened this, I want to go to discriminant and say show script. Again, there are multiple ways to do this. And this opens up the script that you're not responsible to know how it's generated, all right? But up here now, you should have this new table with records to be scored or predicted. And look at this right here. After all, this is why we were doing what we were doing, but I hope that you have a pretty good idea how discriminant works. So if I click run, poof, you get this, and this is the predicted, okay? And if I click and drag this and put it right next to decision, there you go. So this is a yes or no, yes, no, no, yes. Okay, so you can put them right here. Who uses discriminant analysis? Every government spy agency uses that to find spies. Whenever a crime is committed and they find bones, bone fragments, they compare them, especially when things cannot be examined, to eliminate that the bone comes from an animal or not. If they have bone fragments, they do certain analysis. When, sometimes in the news, they do not allow cameras in the court, but allow artists, and somebody describes to the artist the person, and just amazing how these people can draw the rest of the face based on somebody's description of the partial picture of the face. They take that partial and they match it against Interpol's or FBI's or list of criminals, and there are mistakes that are being made, yes, but many times they are dead on. And classifying animals to be of the proper grouping, taxonomy. So discriminant analysis has an immense application in a lot of areas. Here, I have an exercise with which I found on the internet that actually I'm going to add that to your homework 8. I'm doing that. Now, this is from that Said Sayed. You're a manager of a bank and you have a problem discriminating between genuine and counterfeit banknotes. Very nice exercise. So each banknote is described by certain distances, okay? So here's a description. The two classes are yes or no, if the thing is counterfeit or not. Here is, I give you a description of the methodology used, all right? But I am helping you because I am giving you this is the original data. It's a small file. Why does it have a problem opening it? Okay, so I think you can use this one, LDA exercise back notes original. Okay. So you can use this. This is in Excel. And you see, these are actual notes. What is this? You have 200 notes, bank note, BN for bank note. Oh, it opened up the CSV file. This is the original, but I have given you, I've done the work. This is the one that did I forget to include? Well, I forgot to include this column here, counterfeit. I'm going to ask you to add that. All right? Somebody gives you a bad assignment. In this case, it's me. I forgot to, but let's say now that that's how I designed it. I did not. I forgot. Put that column there. This will happen. Okay, just add that column. C141, just take that column and put it over here. I'm doing it in Excel Miner here. But you, I will correct whatever errors are, and I will, within the next, sometime this afternoon, I will fix it, and I will correct it, and I will tell you exactly what to do. The idea is to do linear discriminant analysis, and I don't have, but I will create new records. So here's the idea, and this is actually this is one of the ways that they try to see if the money is counterfeit. They put see, the people that do counterfeit money, somehow they get this machine and they get the measurements, right, and they make perfect money. And the governments try to catch up, and they add something to, like the $100 bill has something, that straight line. So I will give you some new data, and I will ask you to predict if this represents counterfeit money, yes or no. Okay? So this Thursday, we'll have the quiz on KNN. I will send you an email with the new homework 8 sometime this afternoon. I did not plan it, but the two problems that I have up there, so let me just clarify that too. Again, I would have done this work in the last, I had a lot of time, but I just could not think straight. So, assignment 8, these problems actually come from another book, but these problems are self-contained. I will add to that. Okay, and I will give you an extra day. I'll give it to Friday. I'm not here on Fridays, but I'll find some way of having you drop off the homeworks to give them to the TA. Being late with the homework one day or a couple of days, right? I know who's working on it. That doesn't bother me if you're late by a day. By this time, I know who does what, who works in this and that, right? I want to treat you as professionals. I am making it, I want you to work hard because I want you to do well, not just here, but also in life. And these examples are, these exercises are pretty good. Have a great day.